In this video, we're going to look at some of the problems from Chapter 8 and work through some examples. So the first one is asking us to calculate an electrolyte concentration. So the problem says that a laboratory test for a patient indicates a blood calcium level of 8.8 milliequivalents per liter. And we're asked to find how many moles of calcium are in 0.5 liters of blood. And then part B says if chloride is the only other ion present, what would be the concentration? So we start out with the 0.5 liters, and then I am going to line up my units. I have 8.8 milliequivalents per liter, and that came from right up here. So I'm going to put the liters on the bottom and the 8.8 milliequivalents on the top. And the milliequivalents and the the liters would cancel. And then I am trying to find how many equivalents that is, so I'm going to convert my milliequivalents to equivalents, and just like in milligrams, there's 1,000 milliequivalents in one equivalent, so I would cancel out my milliequivalents, and then I just have equivalents. We're then going to take those equivalents and we're going to convert them into moles. So there's the equivalents that I had from the previous part. And then in calcium plus 2, since the charge is 2, that means there's going to be 2 equivalents in 1 mole. So I'm going to take and put my equivalents on the bottom so they cancel, and then that's going to give me my moles of my calcium. Now for part B, it said if chloride is the only other ion present, and we want to know its concentration. We can find its concentration because it's going to be exactly the same, because if calcium plus 2 is 8.8, then chloride must also be 8.8 in order to balance out the charge. Our next example is looking at saturated solutions and unsaturated. So at 20 degrees it says the solubility is 34 grams per 100 grams. So that's my solubility. That's telling me how much it will dissolve. Now, in the lab, I have a student that's missing 75 grams with 200 grams at 20 degrees, and we want to know how much of it will dissolve, if it's saturated or unsaturated. So, I have, it says this is my solubility from before. I am going to start out with 200 grams, because that's telling me how much water I have. So if I can dissolve 34 in 100 grams, then that means I can dissolve 68 if I had 200 grams. Now, because I am trying to dissolve 75 and I can only dissolve 68, that's the only amount I can hold. If I'm trying to dissolve 75, that's more than what it can hold, which means that that is going to be saturated. Now in part C, it wants to know how much is going to settle out. Well, if I added 75 and only 68 would dissolve, the difference between those is 7 grams, and that's going to tell me how much is going to sit at the bottom of the container. In our next problem, we're going to work on writing and balancing equations. So it says NaCl and AgNO3 are mixed. So here's my AgNO3 and my NaCl. And we're going to be a double replacement, so the first two things are going to switch places. So the Ag is going to go with the Cl, and then the Na is going to go with my NO3. Then I'm going to look at my solubility rules to try to decide which one of those is aqueous and solid. So when I look at my solubility rules, it tells me all nitrates are soluble, and anything with column 1 is soluble, so that means that's going to be aqueous. And chlorides, most things are soluble except for silver, mercury, and lead. And since this is silver, that means it's not going to be soluble. So it gets an S. Now, any of the things that are aqueous dissolve in water, and they're going to split apart and form ions. So when I'm writing my ionic equation, I'm going to split apart everything that's aqueous into its ions. So I have a silver ion and a nitrate ion. I have a sodium ion and a chloride ion. This one is not going to separate because it's a solid. It doesn't dissolve. This one separates into the sodium ion and the nitrate ion. Then I look at that, and anything that is the same on both sides I would cancel out. So for example, I have a sodium ion that's the same on both sides. And I also have a nitrate ion that's the same on both sides. Those are called spectator ions, and I can cancel those out. And the pieces that are left, the Ag, the Cl, and the AgCl, that's what's forming my net ionic equation. So that's what I get after I cancel out the spectators. Now for mass percent, we're going to have three that are all going to be very similar. I have percent by mass, percent by volume, and then I have percent mass by volume. And we're going to work a problem with each one of those. So in this case, I have 30 grams of NaOH, and I'm putting it in 120 grams of water. So in order to find the mass percent, I have to put the mass of the solute and divide by the mass of my solution. So I have 30 that's going to go on the top because that's my solute, and I'm dissolving that in 120 grams of water, which means my solution has 120 plus 30 added up. That's the total mass of my solution, is 150. So if I take 30 divided by 150 and I multiply by 100, that's going to get me my percent. And this has three significant figures. This one has 4, so the least amount is 3. So I have 3 significant figures, and that would be 20% by mass. And there was the equation that we were using, where it's percent by mass is grams of the solute over the whole solution and then times 100. This next example is very similar to the percent mass that we were just doing, except this is percent volume. So to find the percent volume, we're going to take the volume of the solute divided by the volume of the solution. So just identical, except before we had masses up here instead of volumes. So in this particular problem, I have a solution that has 59 milliliters of the extract. That solution, that 59 milliliters, contains 49 milliliters of alcohol. So in that case, the 49 milliliters is my solute, and I have a total of 59 milliliters of my solution. So I have 49 milliliters of the alcohol, I have 59 milliliters of the solution altogether. So 49 divided by 59 times 100 would get me my percent. And this has 2 significant figures, and the 59 also has 2, so least amount is 2, and I got 83% by volume. Now my next one is going to be very similar again, except it's percent mass by volume. So in this case, I'm going to take the mass on the top, the grams, and I'm going to divide by the volume on the bottom, which is going to be in milliliters. And I have a solution that has 5 grams of Ki and enough water to give a final volume of 250 milliliters. So I'm going to put my solute on the top, my 5 grams, then I'm going to put my volume in milliliters on the bottom, so 5 grams over the 250 milliliters. And then I'm going to divide and multiply by 100. This one has 2 significant figures, this one also has 2, so my final percent has 2, and it ends up with 2% mass by volume. The next example is using molarity, another way to calculate concentration. And in order to find molarity, I have to take the moles of my solute divided by the liters of my solution. That's the equation that we're going to use. And they want me to find the molarity if I have 60 grams of sodium hydroxide in 0.250 liters of solution. So the first thing I'm going to have to do is find my moles, because I need moles on the top. So I'm going to take my 60 grams, and I'm going to be dividing by the molar mass of NaOH. So 1 Na, 1 O, and 1 H added up. I'm going to put that on the bottom, so those cancel, and that's going to tell me my moles. So I have 1.50 moles of sodium hydroxide. Now to find my molarity, I'm going to take that moles and divide by my liters of solution. So I'm going to take my 1.5 moles, divide by the solution that they gave me, the 0.250 liters, and I'm going to get 6.00 for 3 significant figures, molar sodium hydroxide solution. And this capital M is how I label molarity, and it's pronounced molar. So I have a 6 molar solution. Now in the next example, I'm going to be using my mass percent to help me find my mass. So I have a 1% mass by volume solution, and I want to know how many grams there are if I have 60 milliliters. So I'm going to start out with my 60 milliliters. And then if I have 1%, 1% means per 100. So 1 gram per 100 milliliters. That's because my percent mass by volume is grams over milliliters. I'm going to put the milliliters on the bottom so that those cancel, and I take 60 times 1 and divide by 100, and that's going to get me my mass, so 0.60 grams. Next one is going to be using our molarity that we were practicing on the slide before. And it wants to know how many liters if I have a 2 molar sodium chloride solution and I have 67.3 grams of sodium chloride. So I'm going to use this 67.3 grams, and then I'm going to convert that grams into moles, because in my molarity it has moles. So in order to convert it to moles, I'm going to divide by my molar mass. So 1 Na, 1 Cl added up, that's going to be my molar mass, and I put it on the bottom. My grams will cancel, and that's going to get me moles. Now 2 molar means that I have 2 moles for every 1 liter of solution, because that's what molarity is. And since I had moles here, I need moles on the bottom to cancel, so I'm going to use this as my conversion factor. So my grams cancel, my moles cancel. I'm going to take 67.3 times 1 and divide by 58.5 and 2. This one has 3 significant figures, this one has 3, so my answer has 3, and that's going to tell me how many liters I would need of solution. Now my next one, it's diluting one. So for a dilution, I'm going to use my C1V1 equals C2V2 equation. C stands for my concentration, and V stands for my volume. So I want to know what volume of a 2.5% solution, so I don't know that, the volume, and then I have 50 milliliters of a 12% solution. So the first thing I'm going to do is I'm going to take my equation and I'm going to divide both sides by C2. So that's what's showing you here, and in that way I can solve for the V2, which is the thing that I want. So in order to solve for V2, I'd be taking C1 times V1 and dividing by C2. So now I'm going to plug in the numbers that I have. I'm going to take my V1, which is my 50 milliliters. I'm going to multiply by C1, which is my 12%, and then I'm going to divide by my C2, which is the 2.5. So 50 times 12 divided by 2.5, and I should get 240 milliliters. And this one has 2 significant figures, 3. This one has 2, so I get 2, and that's going to tell me how much of the total solution. Now the next one, I'm going to be using that molarity in a stoichiometry problem. And it says zinc's going to react with HCl to produce ZnCl2 and hydrogen gas. So there's my balanced equation. And I want to know how many liters of a 1.5 molar solution of HCl if I start with 5.32 grams of zinc. Okay, so the first thing, I have to take our grams and convert it to moles. And to do that, I use the molar mass. Then I'm going to do moles of zinc into moles of HCl. And to do that, I'm going to have to use my mole to mole ratio. And finally, once I know my moles of HCl and I know my molarity, I can find my volume. So I'm going to start out with my 5.32 grams of zinc, and the first thing I'm going to have to do is divide by the molar mass to get moles. So here's the molar mass, and I cross out my grams, and that's going to get me moles of zinc. Then I'm going to use my mole ratio. So here's zinc, and the thing that I'm going to is the HCl. So I have 1 mole of zinc for every 2 moles of HCl. I'm going to arrange that conversion factor. I had moles of zinc here, so the moles of zinc goes on the bottom, 1, and I need 2 of the HCl, so it goes on the top, so my moles of zinc cancel. Now I have moles of HCl, and now I can use my molarity, and my molarity is 1.5, which means 1.5 moles per liter. So since I had moles here, I'm going to put the moles down here, 1.5 moles per 1 liter. My moles will cancel, and the only label I have is liters. So 53.2 or 5.32 times 1 times 2 times 1 divided by the 65.4 and the 1.5. and this has 3, and that has 3, so my final answer has 3 significant figures. Alright, the next one, I want to know how many liters if I have a 0.25 molar solution and I'm going to react it with another solution. So in this case, I'm going to have to start with the liters of one thing. I'm going to use my molarity in order to find moles. So I'm using these two things to help me find moles. Once I find moles of the sodium sulfate, I can do a mole ratio to find moles of barium chloride. So there's my mole ratio. And then once I know the moles of barium chloride, I can use that along with my molarity like I did last time to find volume. So I have 0.0325 liters. And I have a 0.160 molar solution, which means that's how many moles I have per liter. So I have that many moles per liter. The liters go on the bottom, so they cancel. Now I have moles of Na2SO4, and to get to barium chloride, the other thing I want, I'm going to look at my equation. So I have one of those for every one of those. So Na2SO4 is on the top, so that means one of the Na2SO4 goes on the bottom. On the top is the 1 mole of BaCl2. So now I have moles of BaCl2, and I have a molarity, which means this many moles per liter. So if that's my moles, I have that many moles per liter. The moles would cancel, and I'm going to take 0.0325 times 0.160, and then divide by my 0.25. And they all have 3 significant figures, so I get 3 significant figures in my answer, and the leading zeros don't count for significant figures. So the 208, that's how I have 3. Now the last one is on solutions which are isotonic, hypotonic, or hypertonic. And I have to decide what's going to happen to a red blood cell if I place it in each one of the solutions. So in the first one, I have a 5% glucose solution. So that means that's the same as the blood cells. So since it's the same, it's isotonic, and that means nothing's going to happen. In the next one, I put it in a solution which is less concentrated than the cell, and it's hypotonic. And in that case, water is going to be entering my red blood cell in order to dilute that concentration, and the blood cell will undergo hemolysis because water is going to be entering the blood cell. If this concentration was more than the blood cell, then that means water would be leaving the cell, and in that case it would shrink down and undergo crenation. And that's the end of the worked examples in Chapter 8.